Welcome to Math 2320. This is section 7.3, where we look at further properties of the Laplace transform. So, in question 1 here, we're using this particular rule, and that is, what is the Laplace transform of e to the at multiplied by a function? Well, what it does is it shifts the Laplace transform of the original function s minus a, the same a that's on e to the at. So, in this question, we've got e to the 9t times t. So here is my f of t is there. And so this is going to shift its Laplace transform s minus 9. The Laplace transform of t is 1 over s squared. And so when we shift it, we get 1 over s minus 9 squared. All right, in question 2. Question 2, we have again e to the at times f of t. So in this case, I've got e to the 1t. All right, so that's going to shift this by 1. I need the Laplace transform for the sine of 5t. Well, the Laplace transform of sine of kt, got the k on the top, k squared on the bottom. All right, so the Laplace transform of sine of 5t is 5 over s squared plus 25. But now when I shift this by s minus 1, I get a s minus 1 in the place that used to be s squared. Okay, so continuing this, we still want to envision some kind of a shifting. But now we're going backwards. We're taking the inverse Laplace transform. Well, let's see. First off, if I take my denominator, I need to complete the square. Now, I complete the square by looking at b. b is minus 10 divided by 2. So minus 10 divided by 2 is minus 5. Minus 5 squared is 25. So I add in the 25. I subtract out the same 25. I'm going to group together the first 3, which is really s minus 5 squared, and the sum of the last 2 gives me this 1. Alternatively, you could have thought of it as take the 26, split it into 25 plus 1, and group the 25 with the first 3. Same thing. All right, so when I'm looking at this problem, I'm now thinking of it as 1 over s minus 5 quantity squared plus 1. But that should start you thinking it looks like 1 over s squared plus 1, which is a sine. And so it's just a shifted sign using the e to the 5t. Alright, in question 4, this process continues. I'm still looking at the denominator, s squared plus 6s plus 10. Alright, so b is 6. 6 divided by 2 is 3. Square it, I get a 9. So I add a 9, subtract a 9. Group together the first 3, which is x plus 3, quantity squared, and the sum of the last 2 is 1. Alright, so that looks pretty promising. Now, the difficulty is if I want to recognize this as a shift, I need to have an s plus 3 on the top to match the s plus 3 squared on the bottom, because I'm hoping to recognize this as a shifted cosine. So I add the 3, subtract the 3, so I don't change anything. But now I've introduced more complexity in the problem. I need to split this now into two pieces. So the first piece I can recognize as a shifted cosine. The second piece is a shifted sine. So we're going to see this difficulty in many places where we have to do this kind of process of adding and subtracting to manipulate it into a form that we can use. All right, in question 5, we want to use our Laplace transform on this first order differential equation with an initial condition. So apply the Laplace transform all the way across. Laplace transform of y prime, we've got that. Y at 0 is 4. Laplace transform of e to the minus 3t is 1 over s plus 3. Alright, so now I'm going to group together the things that have the Laplace transform in it. I've got the minus 4. I take the minus 4 to the right hand side, divide by s plus 3. So I've got a 1 over s plus 3 squared and a 4 over s plus 3. Well, looking at this one, this looks like 1 over s squared, but shifted. That's why it's e to the minus 3tt. And this one is a straightforward e to the minus 3t. So again, keep your formulas near you and learn to recognize what's shifted, what's not shifted, and how to manipulate the formats. In this particular question, we have a second order problem, two initial conditions. Alright, so the Laplace transform of y double prime. Y at 0 is 0. Y prime at 0 is minus 7. So I've got this piece. I've got the piece for the Laplace transform of y prime. Alright, so collecting all these pieces together, I've got this piece. I've got this piece. And so now the Laplace transform of the whole thing, I can fill in the various pieces that we have. And so when I factor out the a part and I move the 7 to the right hand side, alright, we have this situation. So I need to manipulate this to get it into a format that I can take the inverse Laplace transform. Well, same thing as before, complete the square. B is minus 6, b over 2 is minus 3, square it, I get a 9. So you see I've added the 9, subtracted the 9, and so the first 3 is s minus 3 squared, and the minus 9 plus 13, so grouping together the last 2 gives me that piece. And so now I can recognize almost what it is. Well, let's see, it looks like 1 over s squared plus 4. But to really be a sine, I need a 2 on the top. Alright, so put a 2 on the top, put a 2 underneath so that we don't change anything. And so now this piece looks exactly like a shifted sine where k is 2. So here's the shifted part. Here's the constant out in the front. Messy, yes, and again just manipulating till it fits our particular format. Alright, question 7. Question 7 is extremely messy. We have the following situation. I've got a spring and a mass, and it's hanging from the spring. When you attach the mass, it pulls the spring down, and if you let it sit there, it will come to equilibrium. once it stops bouncing a little bit. All right, wherever it stops, that's the position we're calling 0. Moving downward is positive, moving up is negative. So there are lots of things going on in this problem. First off, the weight is released from rest 20 inches above the equilibrium position. Now there's a lot hiding in those words. Released from rest, meaning I'm not bumping it or giving it any initial velocity. That's why x prime of 0 is 0. 20 inches above the equilibrium. Above. Well, above means it's negative. Everything is in the units of feet, so I need to take my minus 20, and again, minus 20 because it's above. Divide that by 12, so I get a minus 5/3 feet. So we have our initial conditions. It stretches the spring from its normal length by 2 feet. So we want to use something called Hooke's law. Hooke's law is the restorative force, and I get K, which is the spring constant. mg is the weight. We have a 4-pound weight, so mg is 4. X is 2 feet, and so I get that my spring constant is 2. All right, what else is hiding? We have a dampening force of 7/8 times the instantaneous velocity. All right, so my basic equation for this dampening process looks like the following. X of t is position. M is mass, so mg is 4. Gravitational constant is 32 feet per second squared, and so m is 1/8. Spring constant was 2, so here's my dampening, spring constant, and mass. My two initial conditions, and so we get a harmless looking differential equation with two initial conditions. Now, solving this by our constant coefficient method with roots and initial conditions would actually be fairly straightforward. With Laplace transforms, in some ways, it makes this problem more difficult. So let's see why. So first off, I take the Laplace transform all the way through of both sides. Getting into the game, my initial conditions. Alright, so once I clean all that up, it doesn't look too bad. And so I'm going to move my terms that don't have a in it to the right hand side. Still doesn't look too bad. So I divide through by this denominator. Alright. And now I start the process of completing the square. Okay, so our initial headaches begin. B is 7. B divided by 2 is not a nice number. It's a fraction. Square it, I get 49/4. So that's the part I'm adding in and subtracting. Alright, and it's plus the 16 that was sitting there. And so if we clean that up a little bit, that's a minus 49/4 plus 16. 16 is 64/4 over 4, and so I get a 15/4. Alright, so once we've done that, I think I'm seeing in here a cosine and a sine. Alright, so I split it up. So right now I'm suspecting a shifted sine and a cosine. Shifted, I get e to the minus 7/2 t. Now that's not surprising because if we would have looked at the original equation, It does have complex roots, and so it should be of the form e to the at sine and cosine of t. Now, here's where the headaches begin. So, in this question, the first piece, to recognize this as a shifted cosine, I need an s plus 7/2 on the top. Okay, we'll put it in, but I got to put it in for s. So that's s plus 7/2 minus 7/2, all in parentheses. Now, to get it out of the parentheses, I want to keep together the minus 5/3 in the first piece. The minus 5/3 times this piece, I'm splitting into another piece. Alright, so yes, there is this cosine part, but now I'm going to get another part I'm going to have to deal with. What about this piece? Well, if I want to recognize this as a shifted sine, let's see, I'm going to need, this is my k squared, so I'm going to need a square root 15 over 2 on the top. No problem, put it there. But then, so that I don't change the problem, I need to take it out. So it's sitting there in the front, it flipped over. So when I multiply, I get a 1. Alright, so doing all of that, I've got the part from my cosine. I've got this piece. Oh wait, it needs another square root 15 over 2 on the top, so I need to divide it out on the front. Here's the second piece. That still looks promising. Alright, so I've got these two which look like sine pieces, but I need to figure out, well, what's going on with this piece and that piece. So let's see. Cleaning it up, I'm going to get a minus 35 square root 15 over 3 times 15, which will reduce to minus 7 square root 15 over 9. Okay, so that's okay. Now, the minus 5/3 in the front here, I'm going to multiply top and bottom by 3 to get it with a denominator of 9 as well. And so finally, when I take the inverse Laplace transform, I've got the shifted cosine part, I've got the shifted sine part, and we get our final answer for x of t. So all of this is x of t. In some ways, the Laplace transform made it, in this case, more difficult. But it does work, just like when we used constant coefficient techniques. Alright, in question 8, we get something new. We have capital U of t minus a, which is the unit step function. It's 0 from 0 to a, and then 1 thereafter. So u of t minus 1, essentially u of t is at the origin, t minus 1 shifts it to the right by 1. So it looks like that. And in this case, I've got the Laplace transform of that times u to the t minus 1. So we have this relationship here, that the Laplace transform of f of t minus a times u of t minus a is e to the as multiplied by the Laplace transform of my original function. Alright, so well, what is my original function? Well, it is f of t is t, because if I plug in t minus 1, I get the shifted one. Alright, and what does that look like? What is t minus 1 times u to the t minus 1? Well, it looks like a function that's 0 up until 1 and then thereafter grows like f of t is t. All right, so the Laplace transform is simply e to the minus s because of this part, the Laplace transform of t, not t minus 1, and I get 1 over s squared. All right, well, what if we do this for the cosine? So we have this relationship that the Laplace transform of g of t times ut minus a is e to the minus as Laplace transform of g, my original g, at t plus a. All right, so in this case, because of the e t minus pi, I get u t minus pi. I get e to the minus pi s, the Laplace transform of g. My g of t is cosine of 6t, but I'm plugging in t plus pi. So g of t plus pi is cosine of 6 times that, so cosine 6t plus 6 pi. We have from trig the cosine of the sum of two angles, so it's the cosine of the first, cosine of the second, minus sine of the first, sine of the second. But we can simplify that. Cosine of 6 pi is 1, sine of 6 pi is 0. So my Laplace transform of g of t plus pi is really the Laplace transform of the cosine of 6t, and that's s over s squared plus 36. And in question 10, we are given this particular function. U of t minus a, remember, is 0 up until a and then 1 thereafter. So the question is, looking at my f of t and looking at here, well, what happened? Well, what happened is the function is not been shifted anywhere. This point didn't get moved over. What happened is it got chopped off or zeroed out. And so what happens is f of t, it's my original function, but it's multiplied by u t minus a, which turns the function off up until a and then continues onward, because onward u there is just 1, so it doesn't change the original function. So lots of good stuff in this section on Laplace transforms.